Okay, so last time we discussed about, we defined the idea of a matrix group, right? We talked about matrix group, and we talked about the idea of a representation. And what we discussed is that matrix groups are defined by a representation called the defining representation, okay? Okay, great. So, so today what we will do is that we will discuss some different kinds of matrix groups, some examples, okay? Today and maybe part of the next lecture. Okay. So the topic is the different kinds of matrix groups. Okay. So we have already met the matrix groups, say GL and R and GL and C. Now, can someone tell me what is the definition, say, of one of these groups? How are they defined? Say, for example, how is this group defined? GL and R. Anyone?
জেনারেল এনক্রস এন ম্যাট্রিক্স যেগুলোর ভ্যালু আসতেছে রিয়েল নাম্বার থেকে
General
লিনিয়ার এনক্রস এন ম্যাট্রিক্স
yeah, good. যেখানে হচ্ছে কি entries are from real numbers, right? Now, is there any restriction on these matrices? So suppose that M was an element of GL and R. Does M have to satisfy any condition?
It can't have a determinant of 0.
Sorry?
It can't have a determinant of 0.
Exactly. That the determinant of M has to be non-zero. Cano? Why is it so?
It has to have an inverse.
Exactly. Otherwise, M inverse won't exist. And M inverse under matrix multiplication is going to give me this, this equation, right? Very good. So similarly, GL and C is exactly the same thing, but now the entries are complex. So what is the dimension of the matrix group GL and R? How many independent parameters are there?
N square minus 1.
Y1 and y minus 1.
The last one has to be such that the determinant isn't 0.
Right. So although this is a restriction, this is not an equation that cuts down on the number of parameters, right? It just tells you something about what kind of manifold it has to be. Right. So if, for example, Amrajyoti, if you look at the dimensionality of SLNR, in that case, the determinant of m equals to 1, that is an equation. But this is an inequality, right? It's not an inequality. It's not a constraint. Well, it is a constraint, but it's not strong enough so that it'll get rid of any of the independent parameters, right? All it is saying is that it is still going to be n squared, but instead of the parameter space being r to the power n squared, we have to subtract from it all those points. Let's call those points, say u, such that u is the, and that u is the locus of points such that the determinant of x is 0. Okay. So this is the space of parameters, but the dimension is still n squared. Is still n squared. Is that clear? So it's like saying, for example, suppose we have a two-dimensional plane. Suppose that something can take 2 values, and suppose that this is my infinite two-dimensional plane. But suppose that we say that x and y, but x can take x and y can take values in R, but y is, say, positive. So in that case, the number of free parameters is still the same, but we don't have access to the whole R2 plane. We just have access to the upper half plane, right? When we have an inequality like that, we actually don't have a reduction of the number of parameters. What we have is that we just have a subset of the initial domain. On the other hand, if we had y equals to, say, mx plus c, then we would have a restriction. This is a very strong condition such that it would restrict us to a one-dimensional subset. Okay, similarly, this condition is not strong enough to eliminate a variable completely, but what it does is that it just gets rid of part of the space of parameters, okay? But the dimension of the space of parameters is the same. Okay, Siddhima, is that clear?
Yes, sir.
Okay. Right. So yeah, of course, this brings us very naturally to the discussion of SLNR. So SLNR is the group of n by n real matrices, say M, such that the determinant of M is 1. And of course, this is going to eliminate one of the variables, right? And so the dimension of SLNR is going to be n squared minus 1. Okay. So there is actually another way of defining SLNR. Okay. So, but to do that, we need to define something called a commutator. Okay. Okay. Let G be a group say group. Now, if say G and H are elements of that group, then the commutator of G and H. So see that we are not working with the Lie algebra. We are working with the group, Lie group. The commutator of G and H will be defined as G inverse H inverse GH. Okay, this is the definition of the commutator. Okay. Now, if I take the group G, L, and R, and I consider all the commutators, and their products, then that generates the group SL and R. Okay, so this is not very obvious, but let's see if this is the case. So suppose I have GH, where both G and H are elements of GL and R. Okay, so obviously by the product, by the closure, this is also an element of GL and R, right? But now if I take the determinant of this commutator, so G, H, but what is the definition of commutator? It's G inverse, H inverse, G of H. But of course, these are all elements of GL and R, so they all have non-zero determinant. But we know that the product of determinant, the determinant of product of matrices is equal to the product of the determinant of the matrices, right? So that means that we'll have determinant of G divided by determinant of G, because the determinant of G inverse is 1 over the determinant of G, right? And then determinant of H divided by the determinant of H, therefore it's 1. So we see that the commutator of all the elements of GL and R have determinant 1. And therefore, all the elements of GL and R, which are of this form, are part of SL and R, right? And not only that, if we have two commutators, say G1, H1, and then G2, H2, this itself is not a commutator, all right? It's just a product of two commutators. For general elements, G1, G2, H1, H2, it's easy to see it is not a commutator. But if we take its determinant, by the very fact that each of this determinant of each of this commutator is 1, we see that the determinant of this thing is also 1. So we see that all the determinants of, let me write this, not all the commutators of GL and R and their products form a set which is the group which is the group SL and R. Okay, so this is an alternative way of defining SL and R. Okay, is it clear what we're trying to do? I've not proved that this is actually a group, but, and I leave that as an exercise for you to do. Okay, but is it clear that the commutator of GLNR form elements of SLNR? Any takers? Do I need to be do I need to re-explain or? Okay. So similarly, we can define SLNC, sorry, to be a subgroup of GLNC in the way that it's generated by the commutators of GLNC. Okay.